Okay. Yeah, just like to welcome everyone to the AIAA Hampton Roads section Young Professionals Technical Excellence Lecture for Spring 2022. Today our speaker is Dr. Joshua Weisberger, and he's going to be speaking about the single source cutoff grid self-aligned focusing Schlieren system, his award-winning paper that he wrote, journal article that he wrote last year. Just to introduce our speaker really quickly, Dr. Weisberger is a research engineer in the Advanced Measurements and Data Systems branch at the NASA Langley Research Center. He received his bachelor's, master's, and PhD from the University of Buffalo. His research area of interest is in non-intrusive optical diagnostic development, including absorption spectroscopy, interferometry, and flow visualization, Schlieren, and shadow graph techniques. And he's the recipient of our 2022 AIAA-HRS Laurent Bement Paper Competition Award. And just to give a quick background about who Laurent Bement was, the annual award is named in honor of him. He was a member of the Hampton Roads section and was a pyrotechnic engineer at NASA Langley for 37 years. He was born in Missoula, Montana, earned a Bachelor of Science degree in electrical engineering from the University of Wyoming in 1963. He was the author of more than 100 technical publications, was awarded at least 17 patents, and served on the colloquium committee. He received a NASA Exceptional Engineering Achievement Medal for significant contributions to pyrotechnic technology, advancing the success of several national and international programs, and his manual for pyrotechnic design, development, and qualification is an agency standard. His friends and colleagues knew him as an enthusiastic and analytical person who had earned the reputation of always asking the first question at any meeting. His significant contributions to the field made a lasting impact on the industry, and his technical inquisitiveness motivated the Hampton Roads section to name the Young Professionals Paper Competition, which aims to recognize innovative technical research in his honor. So without further ado, Dr. Weisberger, you can grab the ball and take over.
Trying to start the video there. There we go. Thank you. Thank you for the introduction. Let me share my screen. There we go. And all righty, pointer option, pointer. All right, thanks for the introduction. And I really appreciate being able to present to everybody today on this work that Brett Baffle and I have been working on for a couple of years now, and for this publication has come out of all that work. And so this is the single source cutoff grid self-aligned focusing Schlieren system, and you'll see what I mean by all those terms in the upcoming slides here. So I think you'd be hard pressed to find anybody in the science community, at least in wind tunnel testing, for example, that hasn't seen images that were taken with conventional Schlieren imaging systems. And so it's been a staple flow visualization.
Can I interrupt you for a second? It sounds like there might be a bandwidth issue. You might want to go ahead and turn off your camera and see if that helps.
No problem. Let me see. Let me stop sharing because I can't access that. So I'm going to do stop the video. I'll share that again. All right, how does this sound now?
Sounds good so far. Sorry for interrupting.
No problem. Yeah, I told you to. So, all right. Yeah. So, and just interrupt me again if there's any issues. So, so the conventional Schlieren imaging that we've been using at, for example, NASA Langley and a few of the wind tunnels you can see in the images at the right. These are just from 3 of the hypersonic wind tunnel facilities. But there's several drawbacks that you can see in these images that are just commonplace when taking conventional Schlieren imaging, such as the window defects. You can see scratches, you can see window pits. There's thermal air currents outside the wind tunnel, for example, HVAC systems, and these are present as these slow moving density gradients that you can see here. There's also the turbulent wall boundary layer. This is probably the one that has the biggest impact on kind of obscuring your flow of interest. And then in certain tunnels, for example, 15-inch Mach 6, there's a shear layer between the free jet core and the ambient tunnel cabin. And so in the early 1940s, or in 1940 itself, focusing Schlieren was first reported, and its main focus is really to isolate the flow imaging to that narrow depth of field that we actually care about near the, for example, wind tunnel center line, and ignore all this other stuff that's outside. And so the original document that first described it was published in 1940 in Danish, and luckily that's the other language that I'm fluent in, so I was able to do a translation last year to make this available to a wider audience. And so in general, the focusing Schlieren comparison with conventional Schlieren are shown kind of in these schematics down here. In this one here, we have the two wind tunnel windows, and we have our density gradients for flow that you can see in these squiggly lines. And what we're really trying to measure are these red squigglies, but the conventional Schlieren integrates everything between the windows and actually some of what's outside the windows as well. So the focusing Schlieren is really trying to isolate these red squiggle lines and get rid of all the stuff that's outside. And so historically, however, focusing Schlieren has been very difficult to do and time consuming to set up, and that limits its practical use, especially in time sensitive situations like wind tunnel testing. And so this is a schematic of a simple focusing Schlieren system, and the hard part here is really matching a source grid to a perfectly aligned and replicated cutoff grid over here. And so the main motivating factor for the work that we were doing was to not require the fabrication and precise alignment of a separate source and cutoff grid. And we also wanted this to be a single-sided imaging technique that doesn't require optical through access in the wind tunnel, because not every wind tunnel facility has two windows opposing each other that give you clear optical access. So here's just a few of the modern focusing Schlieren systems. I don't know how to get rid of this bar up the top here if you can see it. Yeah, this says modern focusing Schlieren systems. And so the first one from the schematic that I showed before was this large field, two-sided optical access focusing Schlieren system. And this one has that separate source and cutoff grid. And typically this is what you'll see being used if someone's doing focusing Schlieren these days. The next implementation was to make this a single-sided focusing Schlieren system where instead of having to send it through wind tunnel windows from one side and catch it on the other side, now you could put up a piece of retroreflective screen and deposit or print or paint your grid lines onto the sheet and then image that with a matched cutoff grid here. But you still have a separate source and a separate cutoff grid. So then instead of printing on the retroreflective screen, the next implementation said, okay, can we just take a source grid and project it onto the screen? Because it takes time to do the painting. And if you want to change the grid, you'd have to take down your retroreflective screen, put up a new one, paint it again. So they're projecting the source grid out and then they're imaging through this matching cutoff grid. But again, you still have two separate grids. So more recently, some cool implementations of the focusing Schlieren system are shown in these next two. And so this one here, instead of having a screen that's printed with something or using a separate grid, now you have a digital display that you can, with a computer, match to the cutoff grid that you're using and adjust this grid so that it's always matched. However, this now needs two-sided access because you can't put a digital display inside of a wind tunnel. And so you can, so then the next implementation of this was then to say, okay, well, now we have a wall, let's get rid of that two-sided access, let's do a single-sided access and project the grid onto the wall, and again, match that to the cutoff grid with the projector. But even with all these, there is still a separate source grid and a separate cutoff grid. And so what we have done, Brett and I were trying to develop this where you only needed a single source cutoff grid. So that's the first part of the title. And so here is the schematic of the system that we were using, that we used for the results that I'll show here in this in these slides. And so I'll just step you through real quick. The light source can be any polarization, and then there's a condenser diffuser lens that generally is just used to condition the light and make it kind of loosely collimate the light for projection through the system. Now this system works on kind of altering the polarization state of the light through the entire system. And so we use a linear polarizer here to linearly polarize the light to linear vertical polarization, that's LVP. And then through a polarizing beam splitter that is fully reflected onto the main optical axis of the system. So it's projected out through our grid, which is a Ronchi ruling. So it's just a regular pattern of opaque grid lines on a transparent glass slide, essentially. And this is transmitted through a polarizing prism. It transmits through unrefracted, and it transmits through, it doesn't change the polarization state. And then at a quarter wave plate that's appropriately oriented, this linear vertical polarization is transformed into right circular polarization. And that passes through the wind tunnel and the density object of interest. And the field lens here is used to image the Rankine ruling onto the retroreflective background. The background then flips the handedness of the right circular polarization to left circular polarization. It passes back through, and through the quarter wave plate, it is then transformed into an orthogonal polarization state, so linear horizontal polarization, and the polarizing prism refracts that linear horizontal polarization slightly, which provides that cutoff or essentially the projected back source grid onto this cutoff grid. And so this grid acts as both the source and cutoff grid. And so that refracted light now passes through, or is allowed to transmit through the polarizing beam splitter, through a linear polarizer to increase the contrast, and into the camera. And so down here at the bottom, you can see just an overview of the system that we had set up, and it's quite a small footprint. The biggest part of this system is honestly the field lens and the camera system, and this is just based off of certain camera lenses that you're using, like a regular Nikon camera lens, for example. So there's two important optic positioning pairs. One is the Rankine ruling with respect to the field lens, so that is projected sharply onto the retro background. Oops. And then the second is the camera positioning with respect to the field lens, such that it images the density object. So in the next slide, where I'm going through some of these results, this is kind of the route that Brett and I was. We asked questions and we tried to answer those questions. So at the top of each slide, you'll see a question that we asked, and we'll go through the results of what we have found. So the first one is obviously, does this system work as it's intended, and what is its depth of field? And so we set up a small scale system that's typical of one of the wind tunnels at Langley, which is the 20-inch box 6. And so we give ourselves maybe a little bit more room just to account for the windows and give us a little bit more leeway. And then we were imaging a helium jet, a small diameter helium jet that was halfway between the lens and the background to mimic where a model would be positioned at the center of a wind tunnel. And so we took these images of the flow from the helium jet. And so this image here at z = 0 is right at the center, at the focus of the system, when we get the nice turbulent structure from the jet. And then as we move the jet away, so this is in the negative direction, that's towards the field lens, and in the positive direction, that's towards the background, we can see that we get good defocusing of the jet structure. And so we get narrow depth of field, good defocusing, strong Schlieren signal. And so the question that we next asked was, how does this compare to an equivalent conventional Schlieren system? We want to make sure that we get images that are equivalent and not worse than what you would get with a conventional system. And so here we constructed both a conventional Schlieren system, lens-based conventional Schlieren system with the same working distances as the focusing Schlieren system. So the ones that the images to focus on here are these two, where essentially we had the helium jet centered in the field of view, and then we took a heat gun to provide this large-scale thermal plume structure, and we put that either right at the retro background or right at one of the lenses of the Schlieren system to kind of simulate a turbulent boundary layer near the wind tunnel window. And so in the conventional Schlieren system down here, you can see that the thermal plume is kind of convoluting the actual helium jet of interest that you're looking at. But if you look at the focusing Schlieren signal, you only get the nice jet right on the center line, and everything that's outside of that centered jet, which includes now the thermal plume, that's filtered out. So in a lot of the hypersonic test facilities, to get the features of interest, they're usually at higher frequencies. And so our question was, since we're using retroreflective material, are we going to have enough light intensity for this high-speed imaging? And so what we did was we, in the lab, tried to find a flow that was high enough speed that we'd be able to tell whether we were able to get anything useful from these high-speed flows. And so we decided to use this electrode spark that generates a fast shock wave. We're imaging with a 640 nanometer laser with an ultra high speed unit so that we can get up to these higher pulse rates. And for imaging to get these higher frame rates, we needed to use a high speed camera, so the Photron SAZ, and we're testing out 4 different camera frame rates. And so what we can see here up at the top left is the 20 kilohertz framing, which is quite fast for any normal Schlieren usage. But here you can see that actually within one frame, the shockwave is already almost outside the field of view. And so as we increase to 100 kilohertz, 400 kilohertz, a megahertz, we see the shockwave becomes better resolved in terms of the time resolution. And so we do, in fact, have sufficient light return for camera framing rates up to at least a megahertz, and we can probably go higher than that. That was just as high as we went. And so the limitation for these higher framing rates is probably actually going to be the usable camera region of interest, because as you go to higher framing rates, you're going to have to decrease your field of view. So we're confident that this can be used for extremely high framing rates within anything that these hypersonic test facilities will need. So now using this at a wind tunnel facility, you're probably going to have windows between your system and between at least your system and the density object of interest. So in the lab, we were using our system up here where there's no windows in between the imaging system and the retro background and the density object. So we're testing with 3 other configurations. One here is with a window in front of the retro background, but nothing in front of the system. I don't know necessarily when you'd ever need this configuration, but it's one of the things that we tested. This one is more typical of the systems that we're going to be using, where there's a window in front of right after the field lens, and then nothing in front of the retro. That's the case if you put the retro background on the wall, if you only have single-sided imaging. And then this is the case if you have 2 windows. This is if you're looking through both of the windows on the wind tunnel and you have optical through axis. And so when the window is in front of the retro background only, you can see that there's no reduction in the image quality from when you have no windows at all. And this is the baseline case that I showed in the initial testing that we had tested with the helium jet. Then when you move the window to after the field lens, now you can see that there's a slight reduction in the contrast from when you have no windows. And then when you have both of the windows in place, now it's about the same as when you have one of the windows in place, a slight reduction in contrast from the no window case. And so you can use this system at normal incidence of wind tunnel windows without noticeable reflections or glare. In conventional Schlieren systems, you can adjust the sensitivity by moving the knife edge in and out. And we wanted to see if we had the same sensitivity adjustment typical of a conventional Schlieren knife edge cutoff percentage. And so the way that, again, you normally do this is you move the knife edge in and out from the focus point of a conventional Schlieren imaging system. But here, the way that we can adjust the cutoff percentage is by moving the Roshan prism along the optic axis relative to the Rankine ruling, because that incoming beam is refracted at an angle. And so there are 4 different situations or 4 different schematics shown at the bottom, showing a typical, quote unquote, ideal 50% cutoff, where the light coming back is cut off at 50%. And then any increase, so plus shift or decrease minus shift, will either, increase or decrease the intensity depending on where you have, where your grid is projected back onto the original Rankine ruling. Then there's 2 other scenarios where you have a dark field imaging, where any shift or any refraction imparted by the density object will increase your intensity. And then you have bright field, where any refraction will cause a decrease in the intensity. And so we just move this Roshan prism incrementally away from the Rankine ruling. And so the first one here is approximately 50% cutoff. Then we move the Roshan prism 2.75 centimeters away. Now we got to a dark field cutoff. Then we moved it a further 2.75 centimeters away, got the other 50% cutoff. And you can see that these 2 are actually different. If you look at right above the heat gun here, you can see this is dark and this is bright. And we moved it further away and we can get the bright field. And so we do have sensitivity adjustment with this, with a simple movement of the Roshan prism. And so the level of adjustment that you get will depend on either the prism refraction angle that you're using, the Rankine grid spacing, line pairs per millimeter, and the separation distance between the Roshan prism and the Rankine ruling. Then we tried to test what type, does the type of the retroreflective background affect the images? Because we were using 7610 for all the images. This is a typical retroreflective material. that's used for a lot of wind tunnel testing because of the high intensity return. You can buy big sheets. So the only change between this was that we put in different types of retroreflective material, and all the images are scaled to the same bounds. So in the left column, you can see different levels of intensity return for different retroreflective materials. And interestingly, the Hillman prismatic, it's a prismatic type of retro material. This one actually has the highest intensity return, higher than the 7610 that we were using. But the background images or the background subtracted images in the right column, they all show similar levels of detail of the turbulent structure. And so that's showing us that you can really use any retro material that you want, or at least that we have tested, depending on what intensity that you require. So then the other question is, since this is a polarization-based system, what influence does the retroreflective material have on the polarization state of the light? And can we use that to our advantage? And so what we did was remove the Roshan prism from the system. And you can see a schematic down here. And then we took images with every retro material, both without, which is in the left column, without the quarter wave plate, and in the right column with the quarter wave plate. And so what we're seeing here is that for 3 of these retro materials, they actually don't alter the polarization state of the light upon reflection. So if we have linearly vertically polarized light going out, the retro does not do anything. It comes back linearly vertically polarized and gets reflected out of the system by the polarizing beam splitter. But there are 2 of the materials that actually act as if they have a built-in retarder. And this means that they don't need the quarter wave plate for imaging. And so what was interesting about this is that if you're really strapped for cash, you can obtain focusing bright field Schlieren images. So you can see in the left column here, with minimal optics. So you don't need the Roshan prism, you don't need the quarter wave plate, and you also don't need the linear polarizer, since those really just are used to increase imaging contrast. So that was an interesting result. At wind tunnel facilities, you'll typically have a high vibration environment when the tunnel is actually running. And so we were asking, how much can the grid be defocused from the background, the retro background, before we lose any meaningful sensitivity? And so we had the system set up. We had an external camera that was imaging the grid on the retro pattern. So these images are from an external camera imaging the retro. This is the 7610 retro. And we tested 4 levels of grid defocus. This is our sharp focus that we've been using for all of our testing. Then we have 2 intermediate focus cases, and then we have a near total defocus. These are just vertical profiles of the grid line shown in these images. And so at the bottom right in these background subtracted images, we can see that the sharp focus obviously provides our normal high contrast image, and the 2 intermediate defocus grids, you can still see the jet structure, but the contrast is reduced. And then in the near total defocus grid, there's still a faint jet visible, but it's not really useful. And so the vibrations at the wind tunnel can cause defocusing of the grid, and it'll reduce the contrast, but you can still get useful imaging. And actually at a test that we've done at wind tunnels since this paper was published, we didn't really see any grid defocusing. Vibrations were really not a problem. Then we actually asked, do we even need the retro? Can we just use a mirror as the background, as a conventional Schlieren? Because we had a couple mirrors lying around in the lab, and we figured, hey, let's just take out the retro, let's throw the mirror in, see what happens. So we took out the retro, put a concave parabolic mirror in its place, and focused the Ronchi into the mirror surface as we would do with the normal retro. And we got the images shown here below. And so at the focus, you get a nice well-defined structure, and you do get the defocusing as you move the jet away from the plane of focus. Although the depth of focus is widened slightly, as you can see, by being -30 to -60, whereas the other one, we were pretty much defocused at -10 for the same size system. We also tested a couple other mirrors, so it didn't just happen that we got lucky with that one mirror. We tested different mirrors, parabolic concave, spherical concave, different focal lengths, different radius of curvature. They also produce similar results shown in here. So you can use existing wind tunnel mirrors if you have optical through access and the mirrors are already sitting there. So that was kind of an interesting result that might not be super useful, but if you wanted to, you could. And then there's a quick note about polarizing prisms here. So the system that I showed in the schematic initially, it works best when the Roshan prism has the same optical characteristics in the forward and the backward direction. So that means that the LVP light we send through should be unrefracted, and it should remain LVP light, regardless of which direction it's going in. And LHP light should transmit refracted through and remain LHP light in either direction. The initial testing that we did with the quartz Roshan prism, that's the one that we have used for all the results throughout this paper. It was showing some weird results. It had some non-ideal properties, and it turns out this is because quartz is a biaxial material. And so what this means for us is that light passing through the prism in the half where it's passing through in the same direction as the optic axis, indicated here with this line, it experiences optical activity, which means that it rotates the polarization, the linear polarization as it passes through. And this means that you get different operation properties in the forward and the backward direction. And since this system is projecting out and back through it, this is non-ideal. So fortunately, we were able to use the quartz prism with good results because this was the initial prism that we had while we were doing this testing. But when we're doing more research, we found a design for a modified Roshan prism from the 1960s that was made out of glass. One half was glass and the other half was quartz. So we ordered one of those. We also ordered a magnesium fluoride Roshan prism because it's a uniaxial crystal. And so we could eliminate this optical activity. So we tested these Roshan prisms using the question, can we use Roshan prisms made from other materials? And since Wollaston prisms it's another polarizing prism, it's used in interferometry quite often. We said, well, people might have these lying around the lab. Can we use a Wollaston prism as well? So in these three images here, you see the glass quartz Roshan prism. This is just another jet. Glass quartz Roshan prism, magnesium fluoride Roshan prism, quartz Wollaston prism. All of these seem like they work well. You can use them with good effect, although as a note down here, you can see the magnesium fluoride Roshan prism looks like it works well. It does. However, in one of the test setups that we used at one of the wind tunnels, we saw that there was some non-ideal polarization characteristics when the light is not collimated passing through it. So what we would suggest for anybody building one of these systems is definitely use the glass quartz Roshan prism. It is the most ideal prism for this particular setup. And then finally, we have recent test facility implementation. So this is after this paper was published. So all the testing shown in the previous slides was performed in the laboratory. And so we said, well, that's all well and good, but can we actually implement this at tunnels? Because that's really what this was made for. So since the paper was published, we've used this at the NASA Langley 20-inch Mach 6, NASA Langley 31-inch Mach 10, and we also took it to the Boeing LCAT ArcJet facility. And so over here at the right, you can see the implementation at the 31-inch Mach 10 tunnel. And this is the windows that we're looking through had to be, they're vertical. So this is on the top of the tunnel. We had to send this system down vertically through the tunnel. And you can see the footprint of the actual main optics, quite small. This is the lens, this is the field lens, and that's the big part of this system. And then of course the SAZ high-speed camera is another huge part of the system. And so the initial testing that we did was actually after a conventional Schlieren testing where we had about an hour to mount the entire system, get it aligned. And this was with only 2 people mounting everything vertically. And so this was the image sequence that we got from that test. We only got one run from that test with the focusing Schlieren before we had to tear down. So this is just an image of a flat plate model injecting into the flow. And there's a cylinder protuberance, and you can see the interaction of the shock and the boundary layer with the bow shock around the cylinder. And so this was motivating for us in the sense that, yes, it does work. This is not ideal. This actually looks like bright field Schlieren, but it is a focusing system. It was easy to set up. It was easy to align with only 2 people. And that was in a particularly difficult wind tunnel to get things kind of mounted and set up. So in the most recent test that we just did, this is again at 31-inch Mach 10. This is with a flat plate with a 30-degree ramp, and we're looking at the transitional shockwave boundary layer interaction. So you can see that these high-speed images, quite nice. It's definitely Schlieren at this point because you see darker and you see lighter regions. You don't have any of that garbage outside in the free stream that are from the tunnel wall boundary layers of the HVAC systems. And so this was another motivating factor for the system actually working the way that we intended. And then we were able to bring it to the Boeing ArcJet facility, which is a really difficult facility to make these measurements. You can't really do any type of flow visualization, Schlieren imaging, but this system was particularly suited for that. And so obviously can't show you results here, but it's in the JANF paper and presentation that's actually that Brett's presenting in about 2 weeks here in Newport News. And so we got really nice results from that. So this is a really nice technique to be able to use in difficult, small optical access wind tunnels. And I believe that is it essentially here. So what did we accomplish? We built this focusing Schlieren system that uses a single optic as both the source and the cutoff grid. So that's the Strongkey ruling here. The retroreflective background ensures the system is self-aligned. So that's where the self-aligned portion comes from in the paper title, because it comes exactly right back on itself. And we've done extensive testing of the optics and configurations for this system. There's more to be done, but we tried to answer as many of our own questions as we could during the testing and writing of this paper. And so for the implementation, we've successfully implemented this at 2 NASA wind tunnels and one of the Boeing's ArcJet facilities. And the hope for this system is that people will start to use the focusing Schlieren system because now it's not as difficult and time consuming to set up. So with that, I will take any questions. I hope I didn't run too far over the time.
That was great. Yeah, thank you, Josh, for that presentation. It's a wealth of research, so I'm actually pretty impressed you can cover it in that short time frame. We are a little bit over time, but happy to have any questions. Does anybody in the participants list have any questions they'd like to pass on to Josh?
Sorry for the sound breaking up again. I just saw that comment.
Okay, so it looks like we have our first Q&A. Janet asked, commented, said, really nice work. How was it funded?
This was funded let's see, it was the T-Cubes, the Transformational Tools and Technologies project, where Brett and I got a lot of our funding to develop some of these systems. And then we kind of take money from a couple other projects, and one of them was the aerodynamic evaluation and testing capabilities, AETC. And then the other project was the plume surface interaction project, because some of this work was funded by essentially the need to do some particle tracking for plume surface interaction testing. And so this measurement technique was almost came about by accident as we were creating a different system to do particle tracking.
Okay, great, thank you. I guess I have a follow-up question. Is there any plans, are there any, I guess, future wind tunnel tests that have already planned to incorporate this technology and give it another test?
Yeah, I mean, the 20-inch Mach 6 testing, we only had about a day to set that up. And so we'd really like to get back in there because we weren't able to get the highest quality that we were hoping for during those tests, but we know that we can get better imaging from the 20-inch Mach 6. The other one, we have future testing also coming back in 31-inch Mach 10, and we probably will be able to go back to the Boeing ArcJet facility for a second phase testing when that happens. We'd like to use this for some of the larger wind tunnels, since I didn't show the slide here, but we did show this could be used for larger fields of view. So we would like to potentially implement this for some testing at the 14x22 wind tunnel. And also there's some upcoming testing at TDT where we're going to be doing some shadow graph, but we did try to see if we could use this as a potential for TDT testing. The only problem there is that the wind tunnel windows or the control room windows really mess with the polarization state. So because these are like ballistic grade glass, so if you look at the stress patterns, they have they just screw up the polarization state. And since this is based off of having, being able to manipulate polarization states throughout the system, it's going to be a little bit more difficult. So really, this is good for use in facilities where you have glass that doesn't change the polarization state as it's being projected through. So we do have opportunities to use this in different facilities, and we're trying to kind of go around and show that it does work in a variety of them, so that it's useful for other researchers at different locations and universities.
Yeah, that's exciting. It's nice to see this all this research coming to fruition and being implemented in all these tunnels. I guess it looks like we have another Q&A from Ray Nolan. Ask, are there any plans to mechanize the setup to scan the field of view?
Yeah, that's a great question. There's a lot of things that we actually want to do to make this kind of a motorized system. So one of them, like you're saying, to essentially get a scan of the focus plane is that you can move your camera. So because the camera here is because the density object that you're viewing is only limited by where your camera is, because that's the camera's position relative to the field lens. So it's viewing this. If you scan the camera backwards, you'll move your plane of focus over here. If you scan it forward, you'll move it over here. So yes, you can put this on a linear motorized stage and be able to scan through during a test. The other things we want to do is we want to add motorized rotation stages for the quarter wave plate. We also want to do it for the Roshan prism, so we can adjust the sensitivity remotely, because a lot of this, when you're doing wind tunnels, you can't just go up there and adjust during a run. You have to be sitting in the control room. So we have plans for putting kind of all these things into their own translation / rotation stages, and yes, adjusting the camera so that we can scan through through the planes of focus for the density object.
Okay. All right. Are there any more questions for Josh before we conclude our talk? Okay. If not, thank you again, Josh, for serving as our Spring 2022 Technical Excellence Lecture speaker. It's fantastic research, and congratulations again on winning our Lawrence Bennett paper competition. And yeah, thank you again. And if anybody has any questions, follow-up questions, I'm sure that maybe Josh can put his contact information in the chat if you'd like to send a follow-up email or have any questions about his research. So thank you
Yeah,
again.
thank you so much. Thanks for having me.
All righty. Thank you all. Thanks for attending.